Hello friends, this is Sonu and today I am going to discuss about adrenergic agonist. So first of all, what is the adrenergic agonist? Adrenergic agonist or adrenergic drug, it first of all it act on the sympathetic nerve system, or we can say that whatever action it's produce, it's similar like the sympathetic nerve system. That's why also can call sympathomimetic. Sympathomimetic. So any drug which belong to sympathomimetic can we see or can we say that it's act on sympathetic nerve system, or it's a produce action similar like the sympathetic nerve system. So in this chapter, first we discuss the main function of the sympathetic nerve system and what types of neurotransmitter it's released and how it's synthesized and how it's create the action. Then we'll discuss receptor, which types of receptor of the adrenergic like adrenergic neuron have which types of receptor in a body where it's localized, what is the main function of the receptor. Then we'll discuss as usual classification, then we'll discuss indication, contraindication, and finally we'll side effects. But I would like to say that before starting the sympathetic function and synthesis, first we'll discuss the receptor and then we'll come back the function of the sympathetic nerve system and synthesis and all things. So first we'll discuss the receptor. Receptor, adrenergic receptor. Adrenergic receptor. First, it's divided into two parts: alpha and beta. And then alpha further divided into alpha 1 and alpha 2. And then beta also further divided beta 1, beta 2 and beta 3. But mainly beta 1 and beta 2, beta 3 is a modified version of the beta 1. So mainly we have to understand about beta 1 and beta 2. Beta 3 is not important because it's the localization of the not too much, just 1 and 2. But before the start the localization, first we should know some logic or some term to easy to memorize the receptor function. Alpha 1 and beta 1, the two are stimulating receptor. A stimulating receptor. And the alpha 2 and beta 2 are inhibiting receptor. Inhibiting receptor. How? Any drug or whenever you stimulate the alpha 1 or beta 1, you can see in the body always will see a stimulating effect. For example, alpha 1. For example, alpha 1 mostly found in a skeletal muscles. So for example, muscles, is it muscles? And alpha 1 receptor is there. So whenever you stimulate the alpha 1, it will be contract, always. It will be contract. Contraction, it means what? Stimulating, you're stimulating the muscle, then it's contraction. That's why the name is stimulating receptor. The same thing in beta 1. Beta 1 most probably it's found in two locations, first in the heart and second in kidney. So let's hear heart. Beta 1. So when we stimulate the beta 1, the cardiac output become increased. How? Because beta 1 stimulate the heart automaticity, contractility, conductivity, the three are stimulating and automatically the cardiac output will become increased. So that's why alpha 1 and beta 1 are stimulating receptor. By this method, if you will understand and if you will remember by this method, then easy to remember the function of the receptor. No need to individually memorize, you can understand very easily. The same thing here, inhibitory. When you stimulate the alpha 2 or beta 2, always you can say the inhibiting function. Let's, for example, beta 2. Beta 2 is a very rich amount, this receptor in found in a very rich amount in a bronchial muscles. So this is the bronchial muscle, and here the beta 2 very highly amounted. So when we stimulate the beta 2, it become inhibit and dilated the muscles. So for example, during the bronchial asthma or any patient who is suffering from COPD, chronic obstruction bronchial obstruction, so on the time the narrowing of the alveoli or narrowing of the bronchial tube. So if you on the time, if you selective drug of the beta 2 receptor which act on the beta 2 receptor, if you apply this drug, it's act on the receptor and the muscles become dilated and narrowing become the area of the narrowing become dilated. Here beta 2 act and the muscles become dilated and the area become too much white, and the patients can feel relief or patient can be normal in these conditions. So that's why beta 2 and alpha 2 is an inhibiting receptor and the alpha 1 beta 1 the stimulating receptor. If you remember this thing, then you will not forget that which one is the stimulate and which one is the inhibit. Now we'll discuss localization of the receptor. How you will remember that in which part of body which types of receptor are there. In here also some logic. First we discuss beta 1 and alpha 1 stimulating receptor. Beta 1 heart and kidney. And kidney. Except heart and kidney, in all body where they found adrenergic receptor, all have alpha 1 receptor. Except heart and kidney and all area of body has alpha 1 receptor. So no need to remember that from where alpha 1 is and from where beta 1. Just you have to remember that heart and kidney have beta 1, and except heart and kidney, in any part of the area where the adrenergic neuron are there, that is alpha 1. I'm talking about stimulating, not inhibiting. I'm talking about stimulating. So for example, in a skeletal muscle, for vascular muscles, or for in a eye, or for any types of muscles, any types of vascular muscles or any types of skeletal muscles has alpha 1 receptor, except heart and kidney. So here you can easy to memorize. No need to remember that where the alpha 1, in which part of the body have alpha 1. If you understand that beta 1 have heart and kidney, and except heart and kidney all have alpha 1. Here also alpha 2 and beta 2. Alpha 2 only found in presynaptic neuron, in platelet, like in a white blood cell, group of white blood cell, platelet, and pancreas. In a pancreas, islets of Langerhans, that is beta cell, is produce insulin. Except presynaptic neuron, platelets, and pancreas of like in a beta cells, except these three, and the rest all have beta 2 receptor. Then all has beta 2 receptor. For inhibiting, this is inhibitory, this is stimulatory. And the beta 3 have exception. Beta 3 just in adipose tissue. So it's not difficult to remember that beta 3 in adipose tissue. Adipose tissue. Again, I will repeat that beta 1 heart and kidney, except beta 1, all uh, all over the body, all area of the body has alpha 1 receptor for the stimulating. Don't forget about inhibiting and stimulating. Alpha 1 and beta 1 are stimulating receptor, and alpha 2 and beta 2 are inhibiting receptor. Beta 3, it's not important to memorize or important to understand, because it's just found in adipose tissue. So it's not too much to worried about the beta 3. Mainly beta 1, beta 2, and alpha 1, alpha 2. So beta 1 and alpha 1 are stimulatory receptor, and it's found beta 1 heart and kidney, except heart and kidney, all area of the body have alpha 1 receptor for the stimulating case. Here for the inhibiting case, alpha 2 in a presynaptic neuron, in a platelets and pancreas, islets of Langerhans, like in beta cells, except these 3 organs, all has beta 2 receptor in inhibiting case. So let's discuss the functions one by one. First discuss alpha 1, like how it will be act on inside the cell, and which types of messenger will be stimulate or inhibit, and then produce stimulating or inhibiting. So alpha 1 is the stimulating receptor. So alpha 1 act on the receptor, that is called 7-path receptor. Means it's 7 times stimulation. That's why it's called 7-path receptor or serpentine receptor. So inside the cell, it's coupled with GQ protein. And GQ protein further stimulate phospholipase C. And here one lipid enzyme, that is called PIP2. Phosphatidyl inositol phosphate. That the name phosphatidyl inositol diphosphate. Whenever it stimulates the PIP2, it further break down in 2 parts, IP3 and diacylglycerol, DAG3. Diacylglycerol. IP3 is inositol triphosphate. And further inositol will go in a endoplasmic reticulum, which is present inside the cell. This is endoplasmic reticulum, and as we know that function of the endoplasmic reticulum, the synthesis of the calcium. So it's stimulate the endoplasmic reticulum and release the calcium. And for the contraction, as we know from the action potential, first it's generate the action potential by opening the sodium potassium channel, and then after the sodium potassium channel, it's eventually influx the calcium, and then muscles become contract. So for the contraction, as we know that alpha 1 is the stimulating neuron, not inhibiting. So when you stimulate, it means if you stimulate the skeletal muscles, it need to contraction, and for the contraction need calcium. So by this way, it's stimulate the GQ protein. GQ will stimulate phospholipase C, and the phospholipase will act on this lipid enzyme PIP2, and then it's further in two part, IP3 and diacylglycerol. So IP3 will go in a endoplasmic reticulum and release calcium, and then calcium will act on the actin and myosin. Actin and myosin. So when we contract the actin myosin, muscles become contract. And the diacylglycerol, it also help to phosphorylation. Like phosphorylation means it help to the influx the calcium into muscles, and will the function become more good or contract become more good. So phosphorylase. So this is for the alpha 1 receptor. This is the main function. Like we can say it's what will happen inside the cell and how it will be contract. So like that it will generate the function. Next we'll discuss the alpha 2. Alpha 2 have little bit difference. Alpha 2 also have 7-path receptor. It's also serpentine receptor, but it's coupled with different types of protein. It's coupled with G inhibitory protein. In alpha 1 case, it's coupled with GQ protein, but in alpha 2 case, it's coupled with GI protein. I mean G inhibitory protein. It's not I, G inhibitory protein. And the G inhibitory protein interrupt the adenylyl cyclase. The function of the adenylyl cyclase become interrupt or diminish, and the adenylyl cyclase will further interrupt the, like it's by the ATP, it's become convert in a cyclic adenomonophosphate. So by the inhibiting of the G inhibitory protein, and then it's become inhibit the adenylyl cyclase, it will not convert ATP to cyclic adenomonophosphate. So inhibit this area, and whenever it inhibit the cyclic adenomonophosphate, it inhibit protein kinase A. Protein kinase A. So protein kinase A will, if inhibit this protein kinase A, means it will not go in a calcium, like in a endoplasmic reticulum, and it will not generate or it will not synthesize the calcium, and then calcium will not influx and muscles become not contract, because for the contraction, for the generating the action potential need calcium, eventually need calcium for the contraction. So it will not produce the release the calcium first. Second, it's open the potassium channel. And as we know, too much potassium will go from intercellular to extracellular, and cell become electronegative. It means what? If cell become too much electronegative, means cell become hyperpolarized. It will not generate action potential. So the function become interrupt, the function become diminished. And as we know that alpha 2 is an inhibitory receptor, not a stimulatory. So inhibitory means the action become inhibit. So it's inhibit by this way. Next we'll discuss the beta receptor. Almost we can say the same function of the main mechanism of the same beta 1, beta 2 and beta 3. First beta 1. The same thing, it's a serpentine receptor. It's G stimulatory protein, but it's act on a G stimulatory. G stimulatory protein. G stimulatory becomes stimulate adenylyl cyclase. Adenylyl cyclase will stimulate cyclic adenomonophosphate by the help of ATP, and the cyclic adenomonophosphate become stimulate protein kinase A. Protein kinase A. And protein kinase A, it releases calcium too much and contract the muscles. But in a beta 2 case, just everything is same, but just here stimulatory, on the beta 2 case inhibitory. G inhibitory, and there they inhibit the conversion of the adenyl cyclase by the cyclic adrenomonophosphate by help of the ATP. So I inhibit, and protein kinase function become inhibit, and the calcium cannot release, and the muscles become dilated. Muscles will not contract, and as we know that beta 2 is the inhibitory receptor, and the beta 3 is just like the beta 1. So this is our the main concept of the receptor. Now we'll discuss the localization. As already I discussed, I said that how you will remember about the localization. So first start from alpha 1 receptor. As I said that alpha 1 receptor is a stimulating receptor. So all types of a skeletal muscle, all skeletal muscles has alpha 1 receptor. Skeletal muscles as well as vascular muscles. Second, for example, all types of a sphincter, all sphincter. A sphincter has alpha 1 receptor. For example, this is urinary bladder as a sphincter. So during the stress or during you running or during fighting, on the time alpha 1 will become a stimulate, and the sphincter is a constrict. Whenever stimulate the alpha 1, a sphincter become constrict, and it's prevent to the urinate. So like that you can understand that alpha how the sphincter will work within stimulation in alpha 1. It's a sphincter becomes stimulate and contracts the stimulus the muscles, a sphincter, and prevent to urinate during the stress or during the fighting or during any action. So it's present in all types of sphincter. As I said, in all muscles, like in the vascular muscles, skeletal muscles. In eye, it's produce mydriasis, and pupil become dilate. Pupil dilate because it contract the radial muscles of the eye, and whenever it's contract the radial muscles, pupil become dilated. So that's what called mydriasis. It's also present in a prostate. And during the alpha 1 stimulation, the prostate become stimulate. So alpha 1, we discussed that what is the main location. Alpha 2. As I said, in alpha 2 present in a presynaptic neuron, in islets of Langer, in a pancreas, or in a platelet. So about the presynaptic neuron, we'll discuss about the presynaptic neuron when we'll discuss the sympathetic system and synthesis of the norepinephrine and epinephrine, how the receptor helps and how it's maintain the synthesis of the epinephrine in a neuron. About pancreas. Actually, for example, during the fighting or during the stress or during the exercise, you need more energy. So on the time the insulin release become slow or become inhibit, because you need too much energy, and energy produced by the glucose. So that's why alpha 2 inhibit or interrupt the function of the beta cells, and the insulin become not released too much by the, and beta cells have alpha 2 receptor. So whenever alpha 2 receptor becomes stimulate, and as we know that alpha 2 have inhibitory neuron, so inhibit the function of beta cell, and beta cells release insulin, so insulin will not release insulin. And the last one, the platelet. Platelets means whenever the platelet cell have alpha 2, so whenever stimulate the alpha 2, it means inhibit the function of the platelet, and its aggregation will there. Aggregation. So alpha 2, alpha 1 we discuss, alpha 2 we discussed. Now discuss beta 1. Beta 1, as I said, that it's found in a kidney and heart. So let's heart. It's heart. Here is the SA node, AV node, and the Purkinje fiber. So beta 1 first is located in a AV node, SA node, AV node, and Purkinje fiber. It means what? When we stimulate the beta 1, increase the automaticity, increase the conductivity, and increase the contractility. You can see. Means the positive chronotropic action. Chronotropic. Positive chromotropic. And positive inotropic. These three types of action you can see in a heart whenever stimulate the beta 1. And second localized in the kidney. What is the function of the kidney? In a kidney, this is nephron. And a kidney have juxtaglomerular apparatus here in a afferent area, and the juxtaglomerular apparatus release renin, and renin it go in a liver, and then it's become renin angiotensin 1, and then angiotensin 1 pass from the lungs, and the lungs have angiotensin converting enzyme, then it becomes angiotensin 2, and angiotensin 2 is a potent vasoconstrictor. It's potent vasoconstriction, as well as produce aldosterone, too much aldosterone, and aldosterone will reabsorb the sodium and maintain the blood pressure. About the this concept, renin angiotensin inhibiting and drug, and the main mechanism, main functions, we'll discuss when we'll discuss the antihypertensive drug. Now just understand that why beta 1 located in the kidney, and what is the main function. The function is produce renin, and renin the maintain the blood pressure. How? Because it's eventually it's produce the angiotensin 2, and angiotensin is a potent vasoconstrictor, as well as it's produce aldosterone, and aldosterone is a huge absorbable of the sodium ion, and sodium ion whenever the huge absorb sodium ion, it's maintain the blood pressure, as well as maintain the iron in the body. So beta 1, heart and kidney, already we discussed, because it's a chronotropic, so increase the contractility of the heart, and blood pressure can be maintained. Now they discuss beta 2. beta 2. Localization of beta 2. First, beta 2 is the inhibiting receptor. So beta 2 widely found in respiratory muscles. Respiratory muscles. For example, any patients have bronchial asthma. Bronchial asthma. This is our bronchial tube. So during the asthma, the area of the bronchial tube is too much narrow. Like for example, is too much narrow, and patients can't breathe properly. So, and as I said that beta 2 is inhibitory neuron, and in the respiratory muscles too much innervated the beta 2 receptor. So if you stimulate the beta 2 receptor, and beta 2 have inhibitory receptor, its tendency to inhibit the any area where the beta 2 is present. So if you stimulate the beta 2, it means what? Muscles become relaxed, and when muscles become relaxed, it will dilate the muscles and dilate the area, and the patient can breathe properly because they dilated the area, because here the narrowing. So beta 2 stimulate and dilate the area. So that's why the beta 2 present in skeletal muscles. First, second, it's produced in it's present in uterus. In a uterus is the exception. For example, it's a uterus. Just for understanding purpose, that it's a uterus. Here the muscle, uterus muscles. So for example, during the pregnancy, this is the normal phenomenon that during the pregnancy, the pregnant lady become too much stress. During pregnancy, the ladies become too much stress. If on the time, if alpha 1 receptor will be there, and as we know that alpha 1 is a stimulating receptor, so it means during the stress, too much noradrenaline and adrenaline release and bind to the alpha 1 receptor, and alpha 1 receptor is a contracting, it's a stimulating receptor, so contract the uterus smooth muscles, and it can be fatal death of the baby, it can be premature baby, or can be abortion could be there. That's why the nature provide here beta 1 during the pregnancy. Beta 2. And whenever during the stress, they bind to the beta 2 receptor, and even in a stress situation, it become dilated, even too much dilated during the stress. So for the pregnant lady, it's better, even it's good. During the stress, it become dilated. But in a normal lady, which is not pregnant, on the time, the amount of the beta 2 is not higher, it's too much. Not too much higher, it's a very little amount, slightly decrease the beta 2. And on the time, alpha 1 become the alpha 1 receptor become there, because in the muscle cell have tendency to, whenever the lady become pregnant, it's produce beta 2 receptor, and where the normal, it can like half of alpha 1 can be produced 50%, and 50% can be beta 2. So these are the exception. Respiratory muscles, uterus, or it can be in all types of skeletal muscle. All types of skeletal muscle, and vascular muscles also. All types of vascular muscle, because in vessels are smooth muscles. And it's also present in adipocyte, that is a fat tissue, so it's increase with decrease the lipolysis because it's a inhibition neuron. And in a beta 3 just one in a adipocyte, beta 3 just present in a adipocyte, fat tissue, fat cell. So let's finish about receptors. We already discussed all types of receptor. Now we'll move in a function of the sympathetic nerve system, and now can easily to understand that how the receptor acts, how to bind and how to produce the action of the sympathetic neurotransmitter. So we already know that in a sympathetic nerve system, main sympathetic transmitter, first is norepinephrine, and the second one is the epinephrine. Also we can say noradrenaline and adrenaline, the both are synonym. So these two neurotransmitter or these two molecule which mainly act on the sympathetic nerve system, but it's from where it's synthesized, how it's synthesized and how it's produced the action, we'll discuss. The initial point of the autonomic nerve system, we can say this sympathetic and parasympathetic in the CNS within the hypothalamus. So let's make CNS. Here's CNS. This area is the hypothalamus. So from here, it's by the descending pathway, it's innervated the sympathetic nerve system, and the sympathetic nerve system is location from thoracic 1 to lumbar 3. So from this area, all area has sympathetic fiber. Let's take one pre-ganglionic neuron. This is a pre-ganglionic neuron, and it's a sympathetic ganglion. And from here, post-ganglionic neuron. Post-ganglionic neuron. Let's move further. This is the presynaptic, and then here, for example, any muscles which start to action, release the norepinephrine and start the action. Some of the fiber go in a adrenal medulla. This is the adrenal medulla, and in adrenal medulla has chromaffin cell. So it stimulates the chromaffin cell and release epinephrine. So eventually the epinephrine will release by the CNS, by the stimulation of the sympathetic fiber system. Here, and one thing also I have to mention that all types of neuron are cholinergic neuron. Any neuron which coming from the CNS, that is the cholinergic neuron. That's why it's release acetylcholine here. Release acetylcholine. And in a post-ganglionic fibers has nicotinic cholinergic receptor. Let's make bigger diagram. For example, this is the pre-ganglionic, this is the post-ganglionic. It's release acetylcholine and here nicotinic cholinergic receptor. So it's bind to the nicotinic cholinergic receptor and start the action potential, and then eventually it's release norepinephrine. Let's begin from starting. From the CNS, it by the descending way, it come from thoracic 1 to lumbar 3. It's a main location of the sympathetic nerve system. And one thing also I have to mention that it's the start the action simultaneously, not like individually, like in some of the sympathetic nerve system must stimulate T1 and T3 and some stimulate the lumbar 1 and lumbar 2. It will stimulate simultaneously in same time. So some of the fiber will go in adrenal medulla and some of the fiber are in the postsynaptic, I mean presynaptic, to release the norepinephrine. So here, as I said, that all neuron which come from the CNS are cholinergic. That's why it's released here acetylcholine in a preganglionic, and the postganglionic neurons has receptor nicotinic-cholinergic receptor. So it's bind to the nicotinic-cholinergic receptor and produce external potential and eventually release norepinephrine, and here it's released epinephrine. Around 80% of the norepinephrine released from the within the neuron in presynaptic, and around 20% of the norepinephrine can be released from the adrenal medulla, and approximately 100% or 95% of the epinephrine released from adrenal medulla. So here discussed like that how from the CNS stimulate and how it's start the action. Now we'll discuss how it's synthesized. What are the enzyme? How it's synthesized, by which enzyme help to the enzyme, and how it's a reuptake and all things. So just take one neuron. This is cell body, this is axon, and this is synaptic vesicles. Here is some target tissue. So the noradrenaline and adrenaline, in a shortcut way, in a nutshell, we can say that it is the endogenous part of the catecholamine. It is related to the endogenous part of the catecholamine, because catecholamine also made by the tyrosine, the help of the tyrosine, and the norepinephrine also it's become released. Finally, it's released by the tyrosine. For example, like it start from protein. From where we can get protein? By the diet. So protein, it further divided into amino acid, and then amino acids have released too much molecule. For example, methionine, valine, and phenylalanine, and as well as tyrosine. So one of the tyrosine by the norepinephrine is made by the tyrosine. So here is the special transporter to transport tyrosine inside the neuron. Tyrosine by the help of tyrosine hydroxylase. That is the enzyme. So by help of this enzyme, it becomes dopa, not dopamine, first dopa. And by the help of dopamine, decarboxylase. Hydroxylase means it's add the hydroxyl group in the structure, and decarboxylase means some of the group will go out. That's why decarboxylase. So by help of the decarboxylase, dopa will convert in a dopamine, and the dopamine should we go in a neuronal vesicles. Why? Because in any cells have mitochondria, because it produces the energy. That's why it should be there in any cell. So mitochondria have produce a special enzyme that is called monoamino oxidase. And if the dopamine will not go in a neuronal vesicles, by the monoamine oxidase it can be destroyed. Monoamine oxidase can be destroy the dopamine. That's why it should go in a neuronal vesicles. But in the neuronal vesicles have a special enzyme that is called dopamine beta hydroxylase. Dopamine beta hydroxylase, or can say oxidase. Sometime in some book written oxidase, but mostly hydroxylase. Dopamine beta hydroxylase. So by help of this enzyme, dopamine will finally convert in a norepinephrine. And then norepinephrine, here's some protein that is called chromographine. Sorry, chromogranin, not graphene. This is the chromogranin. Chromogranin and ascorbic acid and some ATP. So it's bind by this protein and it's concentrate. And then whenever start the action potential, for example, start the action potential, open the sodium potassium channel, and then we'll open the calcium. And whenever calcium influx inside the cell, some of protein are attached to the neuronal vesicles, and some of protein attached in the inside wall of the synaptic membrane. This protein is called synaptic brevin, synaptobrevin, and this protein is called syntaxin. So synaptobrevin and syntaxin. But norepinephrine have to go in outside, like in a synaptic area. So for the go, like it's by the go inside the synaptic vesicles, it need calcium. By the help of calcium. So whenever calcium will come out inside the cell, calcium will attract the both syntaxin and synaptobrevin. So whenever it's attract to each other, here norepinephrine release, norepinephrine become release, and it will come on a synaptic vesicles. So this is our main synthesis. Again, we'll start from beginning. By the protein, it break down amino acid. Amino acid further it divided into huge subgroup. One of the tyrosine. By the help of the tyrosine, it by the transport tyrosine inside the neuron, and the help of the tyrosine hydroxylase, it become convert dopa. By help of the dopamine decarboxylase, it become going dopamine. Dopamine should go inside the neuronal vesicles due to monoamine oxidase enzyme will destroy if will not go in neuronal vesicles. And inside the neuronal vesicles, a specific enzyme that called dopamine beta hydroxylase or oxidase. By the help of this enzyme, it further convert in a norepinephrine, and then norepinephrine, some protein that is chromogranin, ascorbic acid, and ATP. By this protein, it's like attached in this protein and it's concentrate. And whenever the action potential becomes generated, the calcium will influx inside the cell, and some protein which attach in the synaptic vesicle, that is synaptobrevin, and some of the attach in the inside wall of the postsynaptic presynaptic neuron, that is called syntaxin, synaptobrevin and syntaxin. So by the help of the calcium which attached and the release of the norepinephrine in a synaptic vesicle, in a synaptic membrane, synaptic area. Then the further function. Let's stop because more space. So here it's released norepinephrine. But as you know from the physiology, 80% or 85% of the norepinephrine, again it's reuptake inside the cell, inside the neuron, by the special transporter that is called reuptake 1. Reuptake 1, that is the transporter name. By this help of this transporter, norepinephrine will reuptake inside the neuron for the further synthesis, for the further new synthesis of the norepinephrine. Because there are no any specific enzyme to the destroy of the norepinephrine. Some of the enzyme can be, some of the enzyme are there for the destroying, but not too much enzyme. For example, in a parasympathetic nerve system, have acetylcholine esterase. So by this enzyme is destroyed by this acetyl and choline. But here no any specific enzyme to the destroy. That's why it's a reuptake, and the further it synthesizes new protein, new norepinephrine. Now let's discuss the how it acts. For example, here the skeletal muscle. This is skeletal muscle. So alpha 1, as I said, in a skeletal muscle for the contracting alpha 1, beta 1 for the heart, and here for the beta 2 in a respiratory muscles. And as I said during the, when I was discussing the receptor, that alpha 2 also present in a presynaptic membrane. So this is the presynaptic membrane. So presynaptic membrane also present alpha 2. So norepinephrine release, it's bind alpha 1, contract the skeletal muscles, bind alpha 2, increase the cardiac output, bind in a beta 2, relax the bronchial muscles, and also it's bind to the alpha 2 because it's a receptor, so it can bind everywhere where the receptor is there. And as we know that alpha 2 is the inhibiting receptor, it's inhibit. It means what? If the alpha 2 bind norepinephrine here and inhibit the alpha 2, it means it will not create or generate the signal inside the postsynaptic neuron, presynaptic neuron, and then norepinephrine not release in like the synaptic membrane. So what is the main function? That it's a feedback mechanism. Whenever norepinephrine will not there, it means alpha 2 receptor will not stimulate, and as we know that alpha 2 is the inhibitory neuron, so norepinephrine release more and more inside the in a synaptic area. And if the norepinephrine too much release in the synaptic area, it means it bind to the alpha 2, and again with given the signal that too much norepinephrine already released, so please inhibit or prevent the synthesis of the norepinephrine. So we can say it's an auto-inhibitory function or feedback mechanism. It's controlled automatically. Whenever too much norepinephrine release in the synaptic vesicles, it will bind to the alpha 2 receptor, and alpha 2 receptor, as we know that it's an inhibitory receptor, so it automatically give the signal inside the cell, inside the neuron, that too much norepinephrine release, now you stop the releases because too much is already releases. And whenever it's not too much norepinephrine or no any norepinephrine in a synaptic vesicles, it means it will not bind alpha 2, and when further alpha 2 like it give the signal that not any norepinephrine in the synaptic vesicle, so you should start to release. So on the time it's release, start the release. So this is the feedback mechanism or auto inhibitor function that it's generating always. Now we'll discuss some enzyme that how it's destroy. Some of the enzyme, for example, COMT, that is Catechol O methyltransferase. This enzyme name is a Catechol O methyltransferase. This enzyme is too much rich in a liver and too much rich in a kidney, as well as myo also in a kidney and liver. So some of the norepinephrine will not bind and destroy by this enzyme. And some of the norepinephrine will go in a general circulation and eventually it go in a kidney and it go in a liver, and as we know that in a liver too much amount of this enzyme, so on there they can destroy. And some of the norepinephrine, whenever it's a reuptake, it should be go in a neuronal vesicles to prevent the destroy by the monoaminoxidase, but some of miss to go in a neuronal vesicles, so destroy by the myo enzyme and destroy in a cytosol inside the neuron. So these are the main basic function of the sympathetic nerve system, that how norepinephrine and epinephrine release and how it's create the function. So we discussed the all types of receptor, all types of function of the receptor. We discussed the main sympathetic system, function of the sympathetic system, how from the CNS how it's generate, how it's released. In the next session, we'll discuss the classification, and then we'll discuss the main indication, main mechanism. I think we already discussed that drug is act on this mechanism, but we'll discuss again on that time, and we'll discuss the indication, contraindication, and the side effects. So thank you for watching this video. Thank you.